Okay, everyone. Now, these type of examples, these masses going up downhill, we could talk about projectile motions or these simple pendulums. These are simple applications of the conservation of mechanical energy. So, according to this problem, it says there's a mass M connected to a string. It is going down this motion, the swinging motion, the simple harmonic motion, and the length of the wire is given. So one could easily say this whole length from here to here, that should be 1 meters. And this height right here, if you need, this should be 1 minus h, if someone talking about what's going on. Okay, now using our ideas, what we already know, we could say when it reaches the bottom level, this is the potential energy gravitational, or you could say gravitational potential energy U equal 0 level. That's the 0 level. And compared to that, whenever the object is height h above this level right here, when the object is starting, it has a potential energy gravitational equal to m times g times h. That's one thing. And the problem says the object is released from rest right here. V1 equals to 0. That tells us kinetic energy at the starting point equals to a 0. But when the object is moving, when it reaches here, it could have a speed v1. That's what we are going to find. This will have a kinetic energy 1/2 mv1 squared. Now the problem is really, really simple. There's no any friction involved. That is the assumption. Mechanical energy of the system is constant. Mechanical energy initial is equal to E mechanical of the final. Then we can go forward. Mechanical energy, kinetic energy, potential energy, but no springs involved. Kinetic energy right here, 0 at the initial, plus potential energy. Yes, we had m times g times h. That is equal to final situation at the bottom of this swing, 1/2 mv1 squared plus kinetic energy is already considered, potential energy 0. Now we have this situation. We are trying to find v1 equals what? The mass numbers are going to cancel out, m and m cancel out. We are trying to find 2 times g times h square root. That will give you how much is the speed of this object when it reaches the bottom of the hill right here. So one simple scenario, one simple example of these applications. If I go back, we could talk about more information about these. So we talked about this guy, bad, we can leave it. So the problems could include more stuff like this. Part B or C, when it is doing this motion, starting here, goes to here. When it is doing this full motion somewhere here, when it reaches the maximum height, let's say from this 0 level, it is reaching to a level h max. How much is that h max? Still, we can use these ideas to talk about that. When it reaches the maximum height from our previous voyage, we know that V at this location, that's equal to 0. Potential energy, that's equal to m times g times from the 0 level h max, everyone. And again, do the same scenario. Now we can consider initial and final. Now, We can go back to our previous guy, initial and final. Either you could talk about your initial situation right here, final situation right here, initial, and the final. Or you could do, this is your initial situation, this is what you need to find the final situation. If I go with here, it has energy, only the kinetic energy, 1/2 mv1 squared. I am using initial as the very bottom of this motion. No potential energy equals, right here, final is, it has 0 kinetic energy, maximum height velocity 0, plus mgh maximum. Again, mass will cancel out. You are trying to find from the V1, you are trying to find how much is the H max it could go. So different situations, but same idea. Mechanical energy conservation is the tool, the trick we are going to use in these problems.